ಕಾಲೇಜೆಲ್ಲ ಇಂಟರಾಕ್ಟಿವ್ ಟರ್ಮಿನಲ್ ವರ್ಕ್ ಆಗ್ತಾ ಇಲ್ಲ. Hello students, I am Sudha from Telecom Department of Bangalore Institute of Technology. I am here to discuss about the resonance circuit in the new scheme CBCS. We are going to discuss the module 4, which is resonance circuits under 15 EC 34 scheme. What is the objective? We will discuss. We are going to discuss in this module the condition of the resonance in an R, L and C circuit. That is, any circuit which we connect using resistance, inductance and the capacitance. And we discuss about the frequency response of series and parallel resonance circuits, and the cutoff frequency of series and parallel RLC resonance circuits. Also, the half power frequencies, which are called as cutoff frequencies. Quality factor of the circuit, and selectivity and bandwidth of the circuit. The relation between bandwidth and the quality factor. These are the points which we are going to discuss under the objectives of the module 4. And after completion of the course, what are the course outcomes? After completion of this module, the students, you will be able to understand, apply, analyze the basic network concepts, emphasizing the series and parallel combination of passive components. We are dealing with the series and parallel combination of the passive RLC components. So we are going to understand, apply and analyze. We are going to solve certain problems after understanding and applying the concepts. Also, we are going to see the analyzation of the performance of various types of networks using different concepts and principles, such as when you are simplifying the network, you are going to use the various concepts. This is the course outcome for module 4. Now, we define what is the resonance. Resonance is a condition in an RLC circuit. That is, where the network is connected using the resistance, inductance and capacitance, the connected in series or in parallel combination. And resonance is a condition at which the capacitive and inductive reactances are equal in magnitude. Under special condition, the impedance offered by the network is purely resistive, and frequency at which the net reactance of the circuit is 0, we call it as the resonance frequency, and it is the resonance frequency is denoted by the subscript 0 with F0. And at resonance, the general condition is the power factor is unity, which indicates that voltage and current are in phase at resonance. What are the types of resonance circuits we are going to discuss? We are going to discuss two types of resonance circuits. One is the series resonance and the other is the parallel resonance. We will discuss about the series resonance circuit. So, the name indicates what is the series resonance circuit. A series resonance circuit consists of an inductance L, resistance R and capacitance C connected in series. How the circuit looks? This is the combination. R is the resistance. Normally, it is the resistance of the inductance, and these three are connected in series. And we apply a sinusoidal signal of voltage source VAC across the series network. Once the network is connected and the voltage source is applied, the current flows through the circuit. So, the current flowing through the circuit is I, and the impedance of the network is Z, which is a combination of resistance and the reactances of the circuit. Now, again, the resonance condition in AC circuits. There are various methods of achieving the resonance. So, we are going to discuss how the resonance is going to achieve here. It is achieved by varying the frequency of the source. That means we are keeping the voltage constant from the source and varying the frequency of the circuit. Now, we can discuss what is the equation for the total impedance. Now, once the network is connected, the current flowing through the circuit is V by Z, where Z is the impedance of the circuit. We can represent Z is the total impedance, which is a combination of R plus J into XL minus XC, where R is the resistance of the circuit or resistance of the inductor, and XL is the inductive reactance. We represent XL as J omega L, where omega is 2 pi F. So, XL is nothing but J omega L, which is having the units of ohms, and XC is also a units of impedance or ohms, which can be represented as the capacitive reactance, which is XC is equal to 1 by J omega C. And when we substitute this, the total impedance is R plus J into omega L minus 1 by omega C, which represent the impedance is the combination of resistance and the inductive reactance and the capacitive reactance. Now, when the condition of resonance will occur, the circuit is at resonance when the net reactance of the circuit is 0. So, what is the net reactance here? Inductive reactance must be equal to the capacitive R. The XL minus XC must be equal to 0. And frequency of the source is varied to achieve the resonance. Now, what are the parameters we can observe at resonance? At resonance, the net reactance will be 0, which is represented as a point XL is equal to XC, and the impedance of the network is nothing but equal to the series resistance, and impedance will be minimum at resonance. As XL and XC will get cancelled, the total impedance is represented by the resistance, which is called as a dynamic resistance of the circuit. And the current, since the resistance is minimum, the current flowing through the circuit is the V by R, where V is nothing but applied voltage, R is the resistance of the network at resonance. And since the current is maximum at minimum resistance, and current and voltage are in phase, and we can write the power factor as unity. So, this is the condition at the response curve. It is a response curve which indicates the variation of the frequency versus the circuit current. We can see here the frequency response starts at the 0, that is almost equal to 0 frequency, and current will be minimum and it increases to the peak at resonance where the resistance is very minimum, and as we increase the frequency above the cutoff frequency, and the current also will decrease and frequency tends to infinity and current will decrease. So, the response curve indicates that the variation of the current through the circuit with the variation of the frequency, and it is having a maximum at one particular frequency, which we call it as a resonance frequency. Now, we are going to check what is the expression for resonance frequency. So, we know the condition that the frequency is a variable parameter, and as we vary the frequency of the source at a particular frequency, resonance will occur, which we call it as a condition of resonance at which inductive reactance is equal to capacitive. So, at that particular frequency, we define frequency F is the frequency at which we are going to represent as a resonance frequency. So, F will be equal to F naught and omega is equal to F naught, omega naught, where XL equal to XC. When we substitute this condition by equating the net reactance to 0 at F equal to F naught, omega equal to omega naught, we are going to derive the expression for what is the resonance frequency of the series resonance circuit. So, this is achieved by equating the net reactance to 0. That is nothing but XL is equal to XC. As we follow the equation at XL is equal to XC, substitute what is XL. XL is nothing but omega naught, as we are representing omega equal to omega naught at resonance frequency. So, omega naught into L is equal to omega naught C. And on simplification, we can do the cross multiplication, that is omega naught square is equal to 1 by LC, where omega naught equal to 1 by root of LC. So, this is normally we represent omega as radians, and we can represent the frequency as we know that omega naught is equal to 2 pi f naught. So, f naught is nothing but the resonance frequency. So, for a series resonance circuit, the equation for resonance frequency is f naught is equal to 1 by 2 pi root LC. Sometimes while solving the problems, it is not only f naught, we need to find what is the omega naught, or sometimes omega naught will be given in the problems. So, using the omega naught, you need to simplify the circuit. So, the last two equations, that is at resonance omega naught equal to 2 pi f naught radians and f naught equal to 1 by 2 pi root LC hertz. This is the resonance frequency for series resonance circuit, one of the important expression for solving the problems. So, you have to remember this, f naught equal to 1 by 2 pi root LC for a series resonance circuit. As we move to the next, here when we check the frequency response, we know that as the frequency is varied at lower frequencies, that means before reaching the resonance frequency, as we vary the frequency, the capacitive reactance will be dominating, and above the cutoff frequency or resonance frequency, since frequency is very high, XL or the inductive reactance will be very high. Now, here we can check the frequencies at which, this is one of the expression for FL and FC. So, what is FL and FC? So, frequencies at which voltage across the inductor and capacitor are maximum are called FL and FC. So, it is not the resonance frequency, these are the frequencies at which the voltage across the inductor and voltage across the capacitor are maximum. It need not be the resonance condition. So, we are going to derive the expression for FL and FC. Also, we are going to check what is the voltage VC at FC and what is the voltage VL at FL. That is nothing but maximum voltage at frequency FL and voltage at FC. So, we will start with the voltage across the capacitor. So, again, as we know the series circuit which you have the RLC network. So, when we connect the series circuit, okay. So, this is the series resonance circuit at which we are going to, every time any derivation we are going to derive, we use the series resonance circuit. So, in the series resonance circuit, when we check, already we have come across the equation for what is the impedance of the circuit. So, impedance is combination of the resistance and the reactance, that is R plus j omega L minus 1 by omega C. That is the equation 1. Now, in general, other than at resonance, what is the current flowing through the circuit? So, the current flowing through the circuit is nothing but, since it is a single mesh circuit, current is nothing but V by Z. So, on substitution of Z, we have the equation 2, which is current flowing through the circuit at any point is V by R plus j omega L minus 1 by omega C. So, using this equation, we are going to find, using the equation for current and using the relation between the reactance and the current, we are going to find the voltage across the capacitor and also the frequency at which the voltage will be maximum. So, we will start with voltage across the capacitor. Remember, we are going to find frequency at which voltage across inductor and capacitor are maximum, that is FL and FC. So, we are starting, first we will find what is the voltage across the capacitor. So, we know that voltage across any component is nothing but the current into the resistance. Here it is the inductive, when we are taking the capacitor, it is the capacitive reactance. So, equation 3 gives what is the equation for voltage across the capacitor. So Vc is equal to I into Xc. So we know that Xc is equal to 1 by j omega c, and we are going to substitute. It is I into Xc. Xc is 1 by j omega c into I. So the equation 3 will give you what is the voltage across the capacitor, which is I by j omega c. Now we are going to substitute what is the I from equation 2 into the equation 3. So on substitution, it is nothing but 1 by j omega c into the equation 2, that is V by R plus j omega L minus 1 by omega c. So which will give you the voltage across the capacitor, the equation 4. Now once we get the voltage across the capacitor, so we are going to find what is the expression for the Fc. Okay, so using the Vc, we are going to find the maximum voltage at frequency Fc. So for this, I am going to take the magnitude of the voltage. So the magnitude of voltage is nothing but I am taking the root of r square plus omega L minus omega c whole square with the magnitude of the voltage. Next, here to get the condition for what is the maximum voltage at a given frequency, we have to take the derivative of Vc square, since we have the square root in the above equation. So solving this, we will get what is the Fc. Fc is nothing but the frequency at which voltage is maximum across the capacitor. It is 1 by 2 pi of root 1 by Lc minus r square by 2L square. So in this equation, if I take root Lc common, okay, from the equation, if we take the root Lc common, it is 1 by 2 pi root Lc under square root 1 minus r square into c by 2L. And we know that 1 by 2 pi root Lc is nothing but the resonance frequency for a series resonance circuit, which is represented as F0. So we can substitute 1 by 2 pi root Lc is equal to F0. So the equation is reduced to Fc, which is nothing but the frequency across the capacitor, where the voltage across the capacitor is maximum, is equal to F0 into under square root 1 minus r square c by 2L. And we got the equation for voltage as well as the frequency at which capacitance, voltage across the capacitance is maximum. So Fc will give you, remember this equation while solving the equation for Vfc and Vc we require while solving the problems. Okay, next we are going to find the FL, that is, before finding the FL, we must know what is the voltage across the inductor. So the general expression for voltage across the inductor is VL equal to 1 by I into XL, which is nothing but I can take it as I into j omega L, which is given by the equation 1. And again I'll substitute what is I, okay, keeping the j omega L out, substitute what is I is nothing but V by R plus j omega L minus 1 by omega c. So equation 2 will give you what is the VL, which is the voltage across the inductor. Now again take the magnitude of the voltage. So the magnitude of the voltage is nothing but we are taking the under square root, it will be R square plus omega L minus 1 by omega c whole square into the omega L. And what is the VL here? VL is the maximum at frequency Fc. So to get this frequency at which voltage is maximum, we go for the condition, the derivative of the magnitude of VL square and equate that to 0, which will give you the frequency at which voltage is maximum. That can be represented as FL equal to 1 by 2 pi under square root Lc minus r square c square by 2. Once again we can take the Lc common, it will become 1 by 2 pi root Lc, and in conclusion we will get what is the FL, okay, which is nothing but F0 by 1 minus r square c by L. Okay, this is the equation for FL. Now we can check this variation, because this is the general condition where this graph indicates the variation of frequency with the voltage across the various components across the series circuit. So it is plot of VL and VA, VC and the current. So as the frequency is varied, okay, the voltage variation, so at resonance VL equal to VC in magnitude, but they are out of phase. But if you check the curve, the frequency Fc, the voltage across the capacitor is maximum, and we know that the before the resonance frequency, that means between the 0 to F0, the capacitive reactance dominates and voltage across the capacitor is maximum at a frequency Fc where voltage is maximum. Similarly, when you check at F0, F0 is nothing but the resonance frequency. So at resonance frequency, the net reactance will be 0, which is having only the resistance. So it indicates current flowing through the resistance and voltage across the resistance, which is nothing but the supply voltage. So current is maximum and all of the resistance is minimum at F0. Again, as we move above F0, the capacitive reactance will dominate, and as the frequency increases, capacitive reactance increases, and we know that VL is nothing but I into XL. So we get maximum value of voltage across the inductor, which we call it as VL at a frequency FL. So from the graph we can check that above F0 and below F0 we have the two frequencies Fc and Fl where the voltage across the capacitor and inductor are maximum. Now we have a special condition if the resistance, because we know that it is a series RLC circuit. So while designing the circuits, the resistance is nothing but resistance of the coil. So if the resistance is very small, okay, if R is extremely small, then the difference between, that is the Fc, F0 and Fl, if we check, so if R is extremely small, the frequencies Fl and Fc are approximately equal to F0. So while solving the problem, we can check this also. Okay, so we are going to solve a problem to find the voltage across the inductor and capacitor, at which frequency it is maximum, and also what are the voltages across the inductor and capacitor. Okay, this is a numerical where we are going to solve this. It is a circuit, again series RLC circuit. So you can note down the values here. Resistance is 25 ohms and inductance is 0.04 henries and capacitance is given as 0.01 microfarad. Now, what is the applied voltage? 1 volt sinusoidal signal of same frequency as the resonance frequency is to be applied to the circuit. Okay, so here the frequency of the source is taken as the resonance frequency. Now, what are the parameters we are going to calculate? Calculate the frequency at which voltage across the inductor and capacitor are maximum. That is nothing but we are going to find FL and FC. Also calculate the voltage across L and C, that is VL and VC, and the condition given is at resonance frequency. Since the circuit is operating at one frequency, that is the resonance frequency. So remember the parameters. We are going to check here the first we are going to check the frequencies, and also we are going to check voltage across the inductor and the capacitor. So to simplify this problem, we require the resonance frequency, because to find FL or FC we require F0. So we know the equation for a series resonance circuit. The resonant frequency is given as F0 equal to 1 by 2 pi root LC. So on substitution of L and C, we have L equal to 0.04 Henry, C equal to 0.01 microfarad. So on substitution, you will get the frequency of the resonance as 7.95775 kilohertz. I am taking up to the fifth digit because here we are going to check the, it is approaching the resonance frequency. So FL and FC are almost equal to the resonance frequency. Okay, so we calculated the resonance frequency, which is nothing but 7.95775 kilohertz. Next, we are going to find the voltage across the inductor where it is maximum, represented by FL. So we know the equation FL equal to F0 by 1 minus R square C by 2L. So substitute the values of R, L and C. So on simplification, we get F0 by 0.999, which indicates it is very close to the F0, 7.965 kilohertz. You can substitute and check it. It is R square C by 2L. Okay, L is nothing but 0.07, R is 25 and C is 0.0701 microfarad, that is 10 power minus 6. So on simplification, you get the frequency at which voltage across the inductor is maximum, that is FL, 7.965 kilohertz. Next, we are going to find what is the frequency at which voltage across the capacitor is maximum. So it is the same equation, we are just multiplying with F naught. Okay, so Fc is equal to F naught into square root of 1 minus R square C by 2L. So we know F naught is 7.95777, and we know that the under square root 1 minus R square C by 2L is 0.999. So it is nothing but 7.949. So this is both the frequencies. If you check FL and FC, both the frequencies are approximately equal to F naught. Okay, so we have a conclusion in the previous slide that if resistance is very small, so what is the resistance in the network given? It is a 25 ohms. So 25 ohms resistance is very small. So since the resistance is very small, FL and FC, where the voltage across the inductor and capacitor is maximum, these frequencies are approximately equal to F naught. This is the conclusion. Next, we are going to find what is the voltage. Okay, here. So we have at resonance Z equal to R. We know that net reactance will be 0. So when the reactants get cancelled, why we are taking the condition of at resonance? In the problem statement, it is given that the generator is operating at a frequency which is nothing but the resonance frequency. So at resonance, we are finding the impedance, that is nothing but Z is equal to R is equal to 25 ohms. Now, why we require this impedance? Because we need to calculate voltage across the inductor and capacitor, which is in terms of current. So since it is at resonance, we have taken the equation for I equal to I naught. So I naught is nothing but V by R. In general, I equal to V by Z. Since it is at resonance, we have taken I equal to I naught and Z equal to R. So V is already given, so it is taken as 1 volt. So 1 by 25, it is current is 0.04 amps. It is the current at resonance I naught. Now, what is the voltage? Once we know the current, since it is a series RLC circuit, we are going to find voltage across the inductor. So the equation is nothing but it is I naught into XL. So XL is nothing but omega naught L. So we are going to find voltage across the inductor, which is 0.04 into 2 pi into the L, which we have taken as 0.04 henries. So omega naught is nothing but 2 pi F. F is F naught, that is 7.95775 hertz. So on simplification, we get VL equal to 80 volts, and also VC, which is nothing but I naught by omega naught into C, that is current divided by capacitive reactance, I by XC. Okay, so I into, so we are taking here I naught by omega naught into C. Again we get voltage across the capacitor is equal to 80 volts. If you check here, VL and VC are magnified because the applied voltage is 1 volt and it is magnified by 80 times. That magnification factor is called the quality factor. So the same voltage you will get when you find the at resonance Q equal to omega naught into L by R, which is nothing but the voltage across the capacitor is nothing but V into quality factor. So in the circuit, the quality factor is 80. So it is not calculated, but if you can calculate omega naught L by R, which will give you 80. So VC is nothing but 80 into the applied voltage. The applied voltage is 1 volt. So VC and VL at resonance are magnified by the quality factor times. Okay. So this is one of the simplest problem on finding the voltage across the inductor and the capacitor and the corresponding frequency at which voltages are maximum. Okay. So we are going to check here what is the quality factor of a inductor. Okay. So because at resonance, the quality factor of any resonance circuit is nothing but taken as quality factor of an inductor or quality factor of a capacitor. Okay. Okay, so we'll check for quality factor of an inductor as well as the quality factor of a capacitor. So one of it can be used as a equation for quality factor in resonance circuit. In general, what is the definition of quality factor? So as the name indicates that it indicates the quality of the resonance circuit. So as we go for higher quality factor, then bandwidth will become narrow and the frequency response curve will be very narrow. So depending on the application, in some of the applications narrow band filter circuits are required, where we can select the bandwidth in such a way that the quality factor is high, so that bandwidth will be very narrow. So it can be used for a single frequency or very narrow frequencies. So we have a relation between the quality factor and also the bandwidth. We are going to just discuss what is the quality factor of an inductor. So in general, quality factor is nothing but 2 pi, because it is per cycle we calculate, okay, in a circuit. So it is 2 pi into maximum energy stored per cycle by energy dissipated by the resistor per cycle. So it is normally the energy dissipated per cycle. Since the dissipative component here is the resistor, we have taken energy dissipated by the resistor per cycle. So I am giving the quality factor of a inductor. So if you consider the circuit with the inductor, so we are checking the quality factor of an inductor. Which will have only inductance, and part of the resistance of the inductance is the R we are representing, and it is the instantaneous signal which can be represented as Vm sin omega t. Okay, and because it's a single circuit, the current flowing through the circuit. Okay, so when you consider the peak voltage, we consider, by considering the peak current, we can derive the expression for what is the quality factor of a inductive circuit. Now come back to the equation, the quality factor of the inductor. We are going to check what is the Vm. So Vm is nothing but the peak applied voltage. Okay, so the peak, when we apply the voltage as a peak voltage, the corresponding current is Im. So we are going to substitute the two conditions, maximum energy dissipated and maximum energy stored per cycle. That ratio will give you what is the quality factor. So we know that what is the energy stored per cycle in a inductor. It is nothing but half into L into Im square joules. Okay, where Im is nothing but the maximum or peak current of the circuit. So now we need to find, okay, to find what is the energy dissipated by the resistor. We are going to find what is the energy dissipated by the resistor. So it is nothing but we are considering the RMS power. Okay, since it is a resistor, we are considering the RMS value. So our RMS value of the current is nothing but, we write IRMS is equal to Im by root 2. We are writing the equation. So we are going to find the power is nothing but IRMS square into the resistance. This is nothing but we are going to find what is the power dissipated in a resistive circuit. So substitute what is IRMS, it is nothing but Im by root 2 into the resistance. So which we can take it as Im square by 2 into resistance. This is nothing but RMS power dissipated by the resistor. Now we need to find what is the energy. Okay, energy dissipated in the series resistor. So energy dissipated is normally taken as E equal to the power into the time period for one cycle. Power into time period for one cycle. It is again joules. Now per cycle, when we consider, we have T is nothing but time period of one cycle, which can be taken as 1 by F. So I can substitute for the equation for energy, which is nothing but Im square by 2 into R into 1 by F. Okay, it is. So this is nothing but what is the energy dissipated in a resistor. So we have a equation, the equation 1, which will give you what is the energy stored in a resistor, and we have energy dissipated in the resistive circuit. So substitute these two equations, that is equation 1 and equation 2, in the equation for what is the quality factor. So on substitution, okay, you can substitute these two into the equation for quality factor. Okay, the same thing. So you have equation for quality factor. After substitution and simplification, we get Im square by 2 will get cancelled in both the equations, and it is left with the quality factor is nothing but 1 by 2 pi FL, that is omega L by R. So you have on substitution, you have the equation that is nothing but omega L by R. Okay, this is the equation for what is the quality factor of an inductor. Okay, same way you can find the quality factor for the capacitance. Okay, we can find the quality factor of a capacitive circuit. So again, when you check here, again consider the circuit. We can write the capacitive circuit instead of the inductor. I replace the inductor with the capacitance, and once again I am going to find what is the quality factor of a capacitor, because at resonance the quality factor of a circuit can be either quality factor of an inductor or quality factor of a capacitor. So we can redraw the circuit using, it is indicates a loss which gives the dissipation. Again you can consider a network, it is the capacitance C and R, which indicates the dissipation sin omega t, and current flowing through the circuit. Again come back to the equations. You have the equation once again, Vm is the peak applied voltage and Im is the peak current flowing through the circuit. Again the equation for quality factor is 2 pi into maximum energy stored in the capacitor to the maximum energy dissipated in the resistor per cycle. Okay. Now we first find what is the maximum energy stored in the capacitor. So how do you get the equation for maximum energy stored in the capacitor? So you can check here, Q into, we are going to find the current. Okay. So I am going to write the equation for what is the energy stored in the capacitor. So it is nothing but half into C into, okay. So here, now I am going to write this equation in terms of the current, peak current. Okay, it is nothing but half CV square. Okay. Now if I consider this circuit, RLC circuit, so we know that I, okay, when I consider the peak current, so Im is nothing but Vm by Z. Okay. So what is the Z here? Z is nothing but combination of the resistance and capacitive reactance. So I can take here Z equal to R J omega C. Now here I am taking a condition that R is, that is the resistance is far less than omega C. That means the dissipative component is having a resistance which is far less than the capacitive reactance. At this condition I can take Z is approximately equal to the capacitive reactance, that is 1 by omega C. Okay. I can consider Z is approximately equal to the capacitive reactance. Then in place of Z I can substitute what is the Xc. So I can write the equation for what is the current flowing through the circuit. So it is nothing but I am substituting the equation here, which is energy dissipated in the capacitor is equal to half into, write the equation for what is the Im. Okay. So Vmax is nothing but, okay, I'm writing the Vmax. Okay, so Vmax is equal to Im into Xc, which is nothing but Im by omega c. Okay, this is the Vmax. Okay, now come back to find the energy dissipated in the capacitor. I'm finding what is the energy stored in the capacitor. Okay, so you can write it as the energy stored in the capacitor is nothing but half into the C into Vmax, which is nothing but Im by omega c whole square. So here if I expand, it is nothing but half into C into Im square by omega square c. So I can cancel the C and C. So I have here Im square by 2 omega square. Okay, so this is the equation for what is the energy stored in the capacitor. Okay, and we have the same equation for energy dissipated in the resistor. Okay, that is given the energy dissipated. Since energy dissipated equation is same whether it is the RL circuit or RC circuit, so only the equation change is the energy stored in the capacitor, which is nothing but. Now if you check the equation 2, okay, it gives you what is the RMS power dissipated in the resistor. Okay, because we have to substitute in the equation the ratio of 2 pi into the ratio of energy stored in the capacitor per cycle by energy dissipated in the resistor per cycle. So we have the general expression here, P equal to I RMS square into R. RMS is nothing but Im by root 2. So you have the equation for power dissipated in the resistor is Im by root 2 square into R watts. That is the equation 2. And energy dissipated, we are going to find the energy dissipated in a resistor per cycle, which is nothing but the product of P into T, where T is nothing but time period of one cycle, which is equal to 1 by F. Okay, so when you substitute, what is the equation for E equal to P into T, substitute equation 2. So you have energy dissipated in the resistor is nothing but Im by root 2 whole square into R into 1 by F joules. Okay, and on substitution of these two equations, that is energy stored in the capacitor and energy dissipated in the resistor, both these equations can be substituted to get what is the quality factor. So write the equation for quality factor. This is the equation for energy stored in the capacitor and energy dissipated in the resistor. Okay, these two equations I am going to substitute. It is nothing but as already we have taken Im square into RL. Okay, so Im by root 2 whole square into R into 1 by F. Okay, this is the equation for what is the energy dissipated in the resistor. So these two equations I am going to substitute in the equation for what is the quality factor. Leaving these two equations, I will substitute it here. What is the quality factor of the capacitor? It is nothing but 2 pi into the energy stored Im square by 2 omega square divided by the energy dissipated. I take it as a reciprocal, so it is nothing but, okay, so divide by, you can take it as Im square by into R into F. So on simplification we can cancel Im square by 2, so it is left with 2 pi into, okay, omega F into L. On cancellation you will get here it is 2 pi F divided by omega square into R C. Okay, so here 2 pi F is nothing but omega. Here on substitution and simplification you get it is 2 pi, okay, square into F by 2 pi square RC. So you have the equation for what is the expression for the quality factor, which can be given as omega, can cancel here, Im square 2 pi f by omega square RC. Okay. So just write it as 2 pi f by omega square RC, which is nothing but omega by omega square RC. So I can cancel one of the omega. So the quality factor is 1 by omega RC. So quality factor of the capacitor. Okay. So we have already the quality factor of inductor. This is for capacitor. Okay. You have another equation, quality factor. It is omega L by R. This is for inductor. So these two equations, quality factor of a capacitor and quality factor of an inductor, any one of these equation or both these equations can be applicable in a series resonance circuit. Okay. So for a series circuit or inductor and the capacitor circuit, we have quality factor equal to 1 by omega R into C. Okay. Now we are going to check. This is the quality factor of the capacitance. We are going to check at resonance what is the quality factor. As I define, anytime the term resonance comes, we can just substitute that at resonance the f equal to f naught and omega is equal to omega naught and q is represented by q naught. So what is the q here? The quality factor of either an inductor or the capacitor. So in these two equations, last two equations, if I substitute omega equal to omega naught, so it will become q equal to 1 by omega naught into CR or omega naught into L. So omega naught into L by R. So both these equations will give you what is the quality factor at resonance. And the extension of this, we know that omega naught is equal to 1 by root LC. So in terms of the omega, if you substitute 1 by root LC into the equation, so you will get quality factor, the last equation which is indicating the quality factor of a resonance circuit, which is equal to 1 by R root of LC. Okay. So this equation, the quality factor of, so we can write the summary here. Till now we have discussed what is the resonance frequency of a series resonance circuit. So the quality factor at resonance. So we define at resonance f is f naught, omega is omega naught, and we take q is equal to q naught. Now what is q naught? Omega naught into L by R, 1 by omega naught into C into R. These two are the equations for quality factor. And also we can summarize in terms of parameters of the circuit. Quality factor can be written as q naught equal to, I have given the last equation, 1 by R into root of L by C. So these are the equations for quality factor of a resonance circuit. While solving the problem, if you know the resonance frequency, you can use these two equations. If you don't know the resonance frequency in terms of the circuit parameter, you can find the quality factor. And conclusive equation, f naught equal to, you have the equation for the resonance frequency. Okay. These are the quality factor of a circuit which is given. Okay. So we can discuss till now we have discussed only the what is the quality factor. So what is the significance of this quality factor? In the resonance, if you check the resonance curve, as the frequency is varied, current is varying from minimum to maximum at resonance, and once again as the frequency increases, the current is decreasing. So it indicates that the voltage across the inductor and voltage across the capacitor are magnified. So how much is the voltage across the inductor and the capacitor is magnified is given as the voltage magnification factor. Okay. So in general, the voltage across the inductor and voltage across the capacitor at resonance, since at resonance the current is maximum and resistance is minimum, so whatever the applied voltage is there, quality factor times the applied voltage is the voltage magnification factor. So even these equations, that is Vc is taken as I naught into Xc, which is nothing but Xc is 1 by omega naught C. So I naught is V by R at resonance. So if I substitute these two equations for I naught and what is the Xc, I'll get the voltage C across the capacitor at resonance. So this is a very, very important equation, because at resonance, if you can observe the equation, Vc equal to Q naught into V. So V is the applied voltage, Q naught is the magnification factor. So in general, magnification factor will be very, very high. So applied voltage will be magnified by the quality factor times. Same way, we know that at resonance, Vc and VL are equal in magnitude. So VL is also same, I naught into XL, I naught is nothing but V by R, and XL is nothing but omega naught into L. So when you substitute that, you will get omega naught L by R is nothing but quality factor. So you have the equation for VL, which is nothing but voltage across the inductor at resonance, which is magnified by the quality factor times. So you can remember these two equations, that is the magnification factor. Vc at resonance is nothing but quality factor times the applied voltage, and also VL is also nothing but the quality factor times the applied voltage. So V is nothing but applied voltage. So we call the Q is a magnification factor. So the conclusion is, at resonance, the voltage across the inductor and the voltage across the capacitor are amplified by the quality factor times. The reason is, we are considering only the magnitude. If you consider the net reactance, they will get cancelled, but we are considering only the magnitude, which is magnified by the quality factor times. Okay, this is a summary of what we learned today. The resonance frequency, quality factor of a inductor, quality factor of a resonance, and voltage Vc and voltage VL, which is giving you the quality factor times the applied voltage, which we call it as a magnification factor. Okay. So this will give you what is the summary. Now in the coming classes, we can discuss what is a cutoff frequency and also expression for what is the cutoff frequency. These cutoff frequencies in a series resonance circuit, if you check, okay, we have the current is maximum at resonance, and as the frequency varies, at certain point of the frequency, the current is 0.707 times the maximum value. So these are also called as the half power points, because when we consider in terms of the magnitude, it is 0.707 times the maximum value, but when we consider in terms of the power, it is half the maximum power. So these two frequencies at which the power is half the maximum, or at which current is 0.707 times the maximum current, is called cutoff frequencies. So in series resonance, you have two cutoff frequencies, F1 and F2. We will discuss the derivation in next class. Thank you.